Okay, so the properties of water are unique and essential in maintaining the Earth as a hospitable planet. Water is magical because of the atoms involved and how they're arranged in this very simple molecule. But how is the microscopic properties manifested in the macroscopic? So one of the recurring themes in this class is microscopic, that is on the atomic level, versus macroscopic. And once you understand the microscopic, a lot of the macroscopic fall into place. For example, boiling point and freezing point of water, extraordinarily high. Usually boiling point and freezing point depends primarily on molar mass of the atoms involved. And if we looked at water for this, we'd find its boiling point would be about negative 100 degrees Fahrenheit. That is, it would be a gas at room temperature. And we would all be dead. There's no way we could survive if 60% of our body was in a gaseous form. So why is it that the boiling point and also the freezing point are so low? Well, you might want to guess, thinking about what we just talked about, it is because of hydrogen bonding. Right. All right. Another one, density. Think about the density of liquid water versus solid. That is, ice versus liquid. Remember the fact that the pipes freeze in the winter, and this is quite unique. The density, which is the mass per volume. Sometimes people get this mixed up. They just think of it as mass, but it's the old joke, a ton of feathers versus a ton of lead, which weighs more? Well, they weigh the same, but the ton of lead will take up a lot less volume. That is density. All right, so the density of solid water, let's just say ice, is less than the density of liquid water. Usually it's the opposite. Usually in a solid, the atoms are spaced closer to each other, leaving less open pockets, making more mass per volume in the lattice. But for water, we have the hydrogen bonding. Boy, you see a theme here? And this is responsible for large open pockets in ice. Think about this. In a liquid, we have these hydrogen bonds continuously forming and breaking. All right? Liquids flow over each other. Liquids flow. They are not rigidly set. So the hydrogen bonds are forming and breaking. But in a solid, the hydrogen bonds are set, rigid. And it is a beautiful pattern that makes up snowflakes. It is huge hexagonal or six-sided holes in ice that's set up. All right. Last but not least, surface tension. This is why we have water bugs can sit on the top. Without falling down. We also have very um, good waves. That is, the particles stick together. The only other one that's got better surface tension is mercury, and we really don't want to uh, uh, we really don't want to surf on the surface of a deadly poison. Okay, so let's look at the data associated with this. Here now is molecular mass and temperature in Celsius. Okay? If we continue this trend, right, for these are the hydrides, okay, it should continue down this way. Or how about the all these have basically the same formula with group 6. With 2 hydrogen atoms. All right. If we continued this obvious trend, like I say, we would have the boiling point right there. These are boiling points. But instead, all the way up there, due to hydrogen bonding. Now here's my beautiful ice crystal. Let us look. Here is my oxygen and hydrogens in water. Here's the delta positive, delta negative. They put a 2 there. That's okay, I guess. And angstrom is 10 to the minus 8th centimeters. It's very small. But we're just looking at relative numbers. Okay? This is the covalent bond. And you'll notice he's much shorter than the hydrogen bond. Shorter bonds usually stronger the closer the little atoms are to each other. Okay, so you can see that the hydrogen bond's about almost twice as big as the covalent bond. But here is that blow up, but now put into overall repeating units of ice. And look at these large hex holes, large open pockets. Like I say, they're hexagonal, but that's not that important. I just need you to appreciate that this makes a very open structure and reduces the density. The density goes down. The mass per volume. Here are some other things you may not be familiar with. Specific heat. Why does a watch pot never boil? Well, because water has a very high specific heat. Specific heat is the amount of heat necessary to raise the temperature. Heat and temperature are not synonymous. You put a pot of water on a flame, right? You're adding heat. It takes a long time for the temperature to go up from 25 degrees C, which is room temperature, up to, let's say, 100 degrees C, which is boiling. You're continuously adding heat with the flame, but the temperature has an inertia to it. It is slowly in response to the heat raising the temperature. Specific heat is also called heat inertia. And as you might imagine, water has an astoundingly high specific heat. How does this manifest itself in macroscopic properties? Well, we just talked about a watch pot never boils. Well, it does boil, but it takes forever. As opposed to what happens to the metal pot. Think about that. Metal has a very low specific heat. Metal pot heats up at once. It's hard because we use the same terminology in different regards. The metal pot heats up, that is, its temperature increases quickly. And this is due to its low heat inertia, or low specific heat. About 1/10 that of water. All right, so the pot gets damn hot. Oh, excuse me. The pot gets very hot, but the water takes a long time to heat up. This is very good, not just in the kitchen, but around the world. This is responsible for moderation of temperatures. In the oceans don't heat up and cool down quickly in response to the sunshine. It also leads to temperance of temps on the land. That is, the water absorbs a lot of energy without a change in temperature, and this keeps the air cool around the land. This is why, for example, Boston has a lot less fluctuation in temperature than, oh my goodness, Arizona, where you have a very little water in the air to modulate the temperature, and of course no large bodies of water around them. Okay. And remember too that water covers 70% covers 70% of the world, and this water keeps temperature fluctuations within limits that allow living organisms to survive. Also, because organisms consist mostly of water, they are more able to resist changes in their own temperature. So this keeps our bodies kept at a regular temperature. Okay. Shifting phases. When I say phase, I mean a change from state to state, such as liquid to solid, liquid to gas, gas to solid. Evaporation, condensation, and vapor pressure, we can see water also resists evaporation, and this is due to hydrogen bonding. These hold the molecules. How about the molecular neighbors? I want you to appreciate that when you evaporate, You do not break water into hydrogen and oxygen atoms. So it is water resists evaporation and takes a lot of energy to boil. We can measure the amount of heat it takes for liquid water to evaporate using a function called the heat of vaporization. Why is sweating so useful? Well, the amount of energy, say heat energy, needed to convert liquid water into gaseous water, or water vapor, is large. Your skin, heat, provides this energy. So it is removed from your skin, cooling it. So sweating is cooling. As you probably noticed, mostly when a breeze comes up and quickly evaporates the water from your skin. You also might have wondered why citrus growers spray their trees with water when they're predicting that it's going to freeze up that night. This is due to the high heat of fusion, which is what chemists call freezing. And this should be F-U-S, fusion. Okay? As water freezes, we're going the opposite direction now. We're giving off heat energy. And this is absorbed by the fruit. And it does help keep the fruit warm as long as the temperature doesn't go down too far. So this takes energy. This takes energy to change from a liquid to a gas. You have to forcibly break hydrogen bonds and separate molecules far apart if they are in vapor. The opposite, if you went from gas to liquid, condensation, that would give off energy. And here we're going from liquid to solid. This gives off energy. As the hydrogen bonds are formed, they give off the excess energy.